All right, let's go ahead and start our next lesson. We're today going to be studying rational versus irrational numbers, and we'll talk about what that means and then dive into a lot of methods that we have of showing if a number is one of those two things. Before we do that, let's go ahead and start with a quick warm-up, since we've recently been studying square roots and how to simplify them. So what I want you to do is simplify each of these, and I will write the solution out in a moment. So please pause your video now. Okay, so let's go ahead and simplify these three expressions, all involving square roots. So remember, one of our conventions for roots, couldn't think of the word conventions, is to break apart any perfect squares, and our largest possible perfect square that's a factor of 75 is 25. So I'm going to write this, and we know that 25 is square root. 25 is simply 5, so 5 square root 3. Okay? The next one is we don't want square roots on the bottom. That's another convention. Okay? So remember, to deal with that, we just multiply by 1. But of course, 1 takes the form of, in this case, since square root 5 is on the bottom, it helps to multiply by himself because it's going to turn into just 5 and there won't be any more roots. So this becomes 7 square root 5 all over 5. And again, I want to remind you guys, these are just conventions. I don't think that it's anymore as relevant as it used to be, but for some reason they still exist. And let's go ahead and look at the last one. If you recall, we can't just add these together because they are like terms, right? The value under the square root is not identical, but these can be simplified. If we realize 18 is 9 times 2, and 72 is 9. Actually, 9 times 8 is true, but I think there's an even larger perfect square in 72. I thought about 9 times 8, but now I'm thinking about it and I see that 36 times 2 is actually going to be a better choice. And they both have a root 2, so that'll end up being able to combine together. So this gives me 3 root 2 plus 6 root 2, and in total that's going to give me 9 root 2. Now let's move on to the regular part of the lesson. Okay, so let's get into our regular lesson now. A rational number has a very simple and specific definition, and it's focused on this prefix ratio. And a ratio is essentially a comparison between two numbers, but we often express a ratio as a fraction, right? So any number that can be written in the form a over b, where a and b are each integers, is what we call a rational number. Okay? So essentially, can it be written as a fraction? And these top two numbers, the two numbers in the fraction are nice numbers, whole numbers or negatives, or maybe 0. There is one thing we probably should say. B can't be 0, because we recall that you can't divide by 0 and get another number. So that is what we call a rational number. Let's start by looking at some examples of rational numbers. So, first example of a rational number, let's just put it directly in the form of a rational number. You can make anything that looks like this. Okay, notice negative 3 over 5. Both of these are integers, so it's a rational number. That's what it means. Let's look at one that's a little bit more interesting, I guess I would say. How about 0.32? Well, 0.32 is not really in that form, right? But I want to point to something that I underlined here. A number that can be written in that form. It doesn't have to be, because, right, numbers can be expressed in many different forms, so it doesn't have to already be written in that form. Right now, 0.32 isn't in this form, But the good thing is, you probably recall that, maybe I'll use another color here. You probably remember that 0.32 is the same as 32 hundredths, right? This is in the hundredths position, which means it's out of 100. So 32 divided by 100 is the same as 0.32. Now, that is the most direct way of writing it. And guess what? That means it's rational. Of course, we could simplify, right? And this becomes, in fact, actually, what's the largest? They both divide by 4, I think. We divide the top and bottom by 4, we get 8 over 25. So that would be the easiest way, I suppose, to write this in the rational form. Okay? Notice these are both rational and they happen to be equivalent to each other. Next example that I'll give you is actually going to be kind of related to that one. How about 0.32 over 2? That's weird because at first it looks like this number is like almost rational because it's a fraction. But don't forget, this here is not an integer, right? Both of these should be integers. So what do we do with this? What I would invite you to do real quick is just pause the video for a moment and think about it for yourself, okay? And try something out on your own. Okay, now that you've played with this on your own, I trust that you did, I'll say what sticks out to me, but that's not the only way you have to do this. If you were to divide 0.32 in half, you might realize this is the same as 0.16 if you want. And if you do that, then you can see this is 16 over 100, right? 16 hundredths. And if we think about it in a similar way here, it turns out they are also, again, both divisible by 4. And so if we want, we can think of this as 4/25. Okay? Now I want to point you something interesting. This isn't directly about rational numbers, but we always want to be thinking and making sense of things in our heads. Okay? 0.32 was equivalent to 8 over 25. Well, 0.32 over 2, if you thought about this, is really should just be half of whatever we got there, right? So what's half of 8/25? Well, that's just 4/25. So that's pretty nice, huh? Or 32, half of 32 hundredths is 16 hundredths. So either way, it still ends up being, you can see it's half of it. Okay? So those are some examples of rational numbers and I guess some ways we might deal with rational numbers. So what I'm going to do right now is I'm going to put some for you to try, and then you can pause the video and we'll come back and do them again together. So here's the ones that I'll have you try yourself. Okay? So let's try to do 0.1, and let's do negative 0.562. And let's just start with those and have you write them in this form as a rational number. Show that they're rational numbers. Okay, go ahead and pause right now. Okay, so now that you've done the work here, let's just go ahead and check our work. Okay, 8.1 is the same as 81 over 10. Okay, so you want to make sure we're paying attention to which decimal places, or how many decimal places there are, right? This is in the hundredths, but this is only in the tenths. Okay, and this doesn't look like it simplifies any further. This guy right here, well, the negative does it matter? Does it do anything? Yeah, he's just along for the ride here. So 0.562, this 2 is now in what place? It's in the thousandths place, right? And it would be 562 thousandths. And I should have simplified this out ahead of time. I didn't. If you really want, you can simplify this. It doesn't really matter, to be honest, unless we care to show that it's equivalent to something. But if we did divide this in half, that'd be 250 plus 30 is 281 over and half over 500. And looking at that, I don't think this simplifies actually much further than that. Okay, but you can go ahead, you could type this into your calculator and it should simplify it actually for you. So there's our basic of looking at rational versus irrational numbers. So I want to point out an important rule now that we are at this point in our lesson. I think you might be wondering, maybe not, but there is a rule here about rational numbers, okay? And it turns out any terminating decimal. Now, remember the word terminate means like to end something or finish something. So what we're talking about is, if you notice all the decimals we've worked with so far, okay, they're decimals that like, they stop, right? So any terminating decimal actually is rational, okay? That's an important rule. And how do we know that any terminating decimal is rational? Well, if you've kind of thought about what we did so far with each of these examples, in fact, I'll circle the beginning step in all of these, actually this step here, okay? Each of those ended up being able to be written as something over a power of 10. And if you think about that, it makes sense, right? Because when we divide by a power of 10, it doesn't literally move the decimal, but right, we see that the decimal point shifts. And so that's an important rule about rational numbers. Now I want you to think about something here. It's a question I'm going to pose to you, okay? And I want you to actually stop the video and I want you to write down a few thoughts for yourself, okay? What do we do with non-terminating decimals? Okay? Are any of them rational? This is an important question because maybe after we do this other work, we conclude, okay, well, if it doesn't terminate, then it's not going to be rational. But I think if you think hard enough, you might be able to find some decimals that you're familiar with that actually are rational. Okay? Go ahead and pause. Okay, so hopefully you brainstormed a little bit, and I'm hoping you actually thought about some rational numbers you're familiar with that have non-terminating decimals. So I'll start with one example of this actually. The number 1/3. This is a very common fraction that we see, and a lot of you guys regularly tell me that you know 1/3 is 0.333 repeating, right? So in this video, instead of using the little bar on top, I'm going to use an ellipsis there because it's just going to help us with what we're going to do to show that this works, okay? So let's go back to the question. Non-terminating decimals. How can we know if we have a number in the decimal form and it's not terminating, right? So the decimal just continues forever. How can we prove or know if it's actually able to be written in the form of a rational number, meaning if it's rational or not rational? Well, there's a key to this actually, and we'll kind of figure this out as we go through some examples. So example 1, okay, and don't forget to keep writing your notes here. 1/3. We're familiar with that one, but we're going to do something here, and this is the strategy you're going to do for any of these numbers to show that they're rational. We're going to actually call this x, okay? And it's not like it's an unknown value, but what we're going to do is we're going to mess with this equation using our basic moves we've learned, and we're going to actually show that if we solve for x, it can be expressed in a different way. So we know x is 0.333 repeating forever. Watch what I'm going to do here. It's going to be something kind of cool. I'm going to multiply 10 here, but if I multiply 10 there, I have to do it there, right? So what I have is 10x equals 3.33333 repeating forever. Does that make sense to you guys? I guess I'll just put another 3 there, but right? Because this decimal just moves to there when I multiply by 10. And then what I typically do when I'm solving equations is you might be tempted to divide by 10 on both sides, but that's going to get me back to there. I'm going to show you a little trick here, and you can do this for any of these examples. Subtract x, and I'm going to subtract x. And I want to remind you about something from the beginning. I'm going to rewrite this up here. Originally, x was just 0.333 repeating forever, right? So if I subtract x off of here, what I'm left with here is 9x. And remember, x is the same thing as 0.333 repeating forever, right? So what I'm doing is I'm actually just subtracting this part off, and what I get here is 9x equals 3. Now what we can do is what you wanted to do earlier, which is divide by 9, and I get x equals 3 over 9, which is 1/3. That's pretty crazy, huh? We have a method that actually turns a forever decimal into irrational number, okay? But it really depends on something. What it depends on is if there's a pattern in the decimals. Let's go ahead and look at another example of this. Okay, so let's look at a couple more examples of this process. We'll start with this one over here. So we're going to start with the number 0.999 forever. This one's going to turn out to be a little interesting, actually. Let's try it. So we're going to do the same thing. X equals 0.999 repeating, and then we're going to multiply. In this case, we're going to multiply by 10 again. And what we're going to get here is 10x equals 9.999 forever. And then we're going to do the same thing, minus x. And again, don't forget, in our case, x is the same as 0.999. And so this becomes 9x equals, well, 9 minus 0.999, or sorry, 9.999 minus that, just leaves me with 9. And therefore, when I divide both sides by 9, x equals 9 over 9, which is 1. And I don't know if you've ever seen this before, maybe you have, but it's actually true. This is, mathematicians consider this true. If I start out with the number x equals 0.999 repeating forever, it actually is exactly equal to 1. It's a crazy thing, huh? But you'll notice they use the same process. Let's look at this last one here, okay? Now, we still have a pattern. You notice the pattern? Instead of just the same number repeating itself, it's two numbers repeating themselves. So 0.25252525 forever. Well, we're going to set it up the same way, but our initial step will be a little bit different, right? Okay, so if I have 0.2525, however many digits you see repeating, we're actually going to multiply by the power of 10. You see powers of 10 again, like we saw before? That will move the decimal all the way to the end of the pattern, okay, before it repeats. So in this case, there's 2 digits that repeat, so we'll move it to here, and that means I need to actually multiply by 100, not 10. So what I have here is, actually this was wrong. What I have here is 100x equals 25.2525 repeating forever. So again, that 100 moved this decimal place to there, so it becomes 25 point whatever. Now, we're going to do the same thing we did before, but again, remember that 0.252525 was what I started with originally, and we'll leave that up there just for us to remember. And let's do the same thing we did before. Let's subtract off an x and an x here, but don't forget that our x is 0.2525, okay? And this 100 I multiplied is what makes it important that it works this way. And here I get 9x, you see that? 99x, okay? Because 100x is minus 1x is 99. And then if I subtract just the decimal part off, that's what the x does, then what I'm left with is just 25. And therefore x equals 25 over 99. Is that interesting? Okay, so look really carefully here. 0.25252525 repeating forever turns out to be equivalent to 25 over 99. And I want you to think about something here, because if we notice this one, back to the other example, we ended up multiplying by 10 in this one to make this work out for me. And if you probably realize, if I just had 0.3 and it didn't repeat forever, that's the same as 3/10, right? 0.3 repeating forever became 3/9. You see, 3/9 is really close to 3/10. It's just one number below 10 on the denominator. Watch this. If I had 0.25 not repeating, that's 25 over 100, right? Does that make sense? But if I have 0.2525 repeating forever, the two fives, then it actually becomes 25 over 99. So that 99 is one less in the denominator than the 100. So there's really interesting patterns, okay? I'll have you practice a couple yourself right now. The ones I want you to do for yourselves real quick is go ahead and do 0.8181 repeating forever. You might notice the pattern, you might be able to skip to the end. And let's try 0.538538 repeating forever. Go ahead and pause the video real quick and try these. Okay, let's do these together. And we're going to do these quickly so we can get through this. All right, so 0.8181 repeating. Again, we'll assign this to be equal to x. And we're going to multiply this one by 100 because there are two digits repeating. So 100, and what I get is 100x equals to 81.8181 repeating forever. And we're going to subtract x away, and that's going to subtract off all the rest of those decimals. And so I get 99x equals just 81, and so x equals 81 over 99, okay? Now this one, hopefully you notice, has 3 repeating decimals. And so I'm going to go ahead and multiply not by 100 anymore, but by 1,000 on both sides. So 1,000x equals 538.538 repeating forever. And same deal, just minus x again, and minus x again, because x is just the decimal part, right? So that's just going to subtract all that off, and I get 999, x equals 538, and so I get 538 instead of over 1,000, 538 over 999. So there is how we can deal with non-terminating decimals. Okay, let's go ahead and finish off by writing a rule and then jumping into a few other kinds of numbers. Okay, so now we're ready for our second rule for today. What if we have a non-terminating decimal? Well, a non-terminating decimal will be rational if the initial sequence of digits repeats itself. And I should say, if it repeats itself and stops, you know, of course, but forever is what I should say there, okay? Now, I'm not interacting with you right now in person, so, but you may be wondering, all the ones we did were 0 point something. But just think, if I had like 2.8787, let's say, repeating forever, it's just the same as 2 plus 0.8787 forever. So that whole number in the front can still be the same way. It's just, it can be left in the front and then deal with the other part of it, and it's still rational, okay? And that should be okay. Well, here's what I want to look at with you next, and this will be the last part of our lesson for today. This is a famous non-example, and this has some really deep history to it. So you've probably heard of Pythagoras in history. He was a famous Greek mathematician, but if you didn't know, Pythagoras ran a cult, basically. It was basically a religion that worshipped numbers. The ancient Greeks actually believed that numbers were in everything, but they believed every single number was either an integer or it was rational. And since we've been talking about rational numbers, all we've talked about today is numbers that are rational, okay? The Greeks thought every single number that existed was rational. But then one of their own people came along one day and came up with an argument or reasoning to show one particular number wasn't rational. And this is a very famous non-example. let's say we take a square, okay? So we're gonna say this is a square, okay? Which means it has all equal side lengths and right angles. And let's just use this as our unit square, okay? If it's our unit square, then it has side lengths 1. Well, it turns out the Greeks thought every measurement in a shape or around the earth or anything was able to be measured by a rational number, which means if you just cross the diagonal here, it should be rational. Well, if we put an x here, let's say, because let's just say we want to know how long that diagonal is, and if we use something we're familiar with in right triangles, in fact it's named after Pythagoras, the Pythagorean theorem, well, we know that 1 squared plus 1 squared is equal to x squared. And this just becomes 1 plus 1, so 2 equals x squared. And on both sides here, to undo the square, if I use the square root, x equals the square root of 2. And it turns out that this famous non-example is the square root of 2. And that particular value, I'll save it for a later time, but there is a way we can actually prove that this is not rational. And in fact, there are a lot of square roots that are rational, right? So if I look at square roots that are rational, let's say the square root of 9, okay? I think we know that this is 3, and even though 3 is just an integer itself, you probably realize it's 3 over 1, or 6 over 2, or whatever. So that is rational, actually. Or even something like this, the square root of 9 over 4. We can apply the square root to the top and bottom separately, and it becomes 3 over 2. That's still rational. But not rational examples of numbers and square roots, you'll notice these numbers, or even something like 25, right? All these are nice perfect squares under the roots, but when we get things like square root 2, square root 3, square root 5, etc., these numbers that don't simplify nicely, they're not themselves perfect squares, it turns out they all happen to be irrational. And some other famous non-examples would be something like pi, okay? And if you remember, pi is essentially the circumference of a circle is pi times the diameter, which means pi is the circumference divided by the diameter of any circle. These are all important non-examples of rational numbers. We will later go ahead and prove, this will be something I give you as optional, why the square root of 2 is not rational. Anyway, that's our lesson for today, and we'll see you next time.